stuff. So you did the online lesson for Taylor polynomials and Taylor series. So you already have an idea of what those are. Well, before I talk about those, I'm actually going to talk about power series, which is actually 8.6. So that's the lesson that you haven't gone through yet. But again, I don't think it's going to be an issue. I think you're going to pick up on the stuff that I want to make sure you know from 8.6 really quick. So let's talk about power series. Okay, power series. What is a power series? It's a generalized version of a geometric series. So what does that look like? Well, it's an infinite series. C sub n represents the coefficient, which could take on a lot of different forms. So when you looked at Taylor series are power series. They're a specific case of power series. So you're not completely unfamiliar with power series. When you did Taylor series, you were doing a specific form of power series. So the book goes more specific to general. I like to go general to specific in the way I present it, because there's going to be some stuff from power series that I want to do with you as we look at the Taylor series. It's pretty cool. This reason I really like these sections is they really start to make the previous sections make sense. Why did we care so much about convergence and divergence? Now, x's are variables. So again, this is a power function, meaning that it accepts an input for x and gives out a unique output. So if we were to fix x, say let x equal 2, then all we get is a series. That series can be checked for convergence or divergence based on what we did in 8.3 and 8.4. So, for example, let's take a look at this power series. And the question becomes, where does it converge? All right, so here's our example. So 2x plus 3 to the n over n equals 1 to infinity. All right, here's the nice thing about power series. To determine where they converge and diverge for what values of x, we don't have to worry about which test we're going to use. So if I bring up our tests from before, we're not worried about which test. We go right to the ratio test. And so for power series, right here, and again, you're going to get this for the final exam, so you don't have to memorize any of this stuff. I'm going to talk to you about what all of this means. But what we do is this is basically the ratio test right here. So that ratio test we were doing in the last section, every time you check for where a power series converges, you run the ratio test. So let's see how that looks. All right, so we've talked about the ratio test before. We're doing the limit as n goes to infinity of, remember it's a sub n plus 1, 2x plus 3 to the n plus 1 over n plus 1. And then we multiply by the reverse of our general term, n over 2x plus 3 to the n. And we're going to do our canceling, but before, when we were working on these, I said, hey, don't worry about the absolute value that's in the ratio test. So let's go back. This absolute value here becomes a little bit more important when we're testing power series because of that x. So we do want to include those absolute values. You guys, as always, as I'm going through this, if you have any questions about any steps or anything, let me know. Throw it in chat, turn on your mic, let me know. Again, what we want to know is a power series is just a more generalized version of a geometric series where the C sub n is any constant. So we have a power series here. The biggest difference between what we're doing now and what we did previously is this x. Now it's a function. It's no longer just a series of numbers. Okay, now we're going to work with our ratio test. Well, the same kind of canceling occurs. I have n plus 1, 2x plus 3s here, and I've got n of them down here. So that's going to cancel all of these out except for 1. Remember, we looked at this kind of canceling the other day. So 2x plus 3 to the n plus 1 is equal to 2x plus 3 to the n times 2x plus 3, okay? Just the property of exponents. So there's our cancel. Nothing we can really cancel out here. That's fine. Now, here's what I like to do next, actually. Let's take this out of here for a second. The part that depends on n needs to stay inside the limit. But if you have stuff that doesn't depend on n, it does not. So this 2x plus 3 does not depend on n. So I'm going to pull that part out. Absolute value of 2x plus 3. And then what are we left with inside the limit? Limit as n goes to infinity of n over n plus 1. Don't need the absolute value here. It's not going to make it wrong if you have it, but n's always going to be, n's going from 1 to infinity. So this is always positive. Don't really need it. So then the question becomes, all right, what is this limit? Well, we've got a rational expression. So it's the ratio of the lead coefficients, which is n over n. So that limit is just 1. So all this comes out to be is the absolute value of 2x plus 3 times 1, which we don't have to write. Now, so now with the ratio test in the previous section, what we would do is we would check to see if that limit, once we took it, was less than 1, greater than 1, or equal to 1, right? We don't do that anymore. We're making the power series converge. In other words, we're finding what values of x make it converge. All power series will converge at least a single point, and that would be whatever point makes the whole thing 0. So like -3/2 makes this whole thing 0. So worst case scenario, it converges at 1 point. Now, we'll look at all 3 cases too. What we do though is we know this converges if this is less than 1. So what we need to do is solve this absolute value inequality. Couple different ways you can do that, but for the absolute value of 2x plus 3 to be less than 1, that means 2x plus 3, well, it must be less than 1, but it also must be greater than -1. All right? So it might be a while since you've solved absolute value inequalities. You're going to get plenty of practice in 8-6. So don't worry. So it'll come back to you. So that setup is that's how we set it up. And what we do is we solve for x just like we would an equation. We want x isolated. So we'll subtract 3 from all of these. So -4 is less than 2x is less than -2, excuse me. And finally, we divide by 2. And so what we get is that x has to be in between -1 and -2. So this is what's called an interval of convergence. And we'll define that in this slide here in a second. Interval of convergence. Because it's an interval over which our power series converges. Because as long as x is in between -2 and -1, the ratio test is going to come out less than 1. Now, there is something we need to check. If we go back to our thing here, remember, the ratio test is inconclusive if the limit is equal to 1. Well, the limit is equal to 1 at both of these endpoints. So whenever you're doing an interval of convergence, you have to check the endpoints. Okay? We have two of them. We have one at x equals -1. And what we do is we plug that into our power series and simplify. So if x equals -1, then our power series becomes 2 times -1 plus 3 to the n over n. This is a -2 plus 3 is 1. 1 to the n is just 1. So this whole thing simplifies down to the series 1 over n. This is a series we've seen before. We know something about this series. This is our harmonic series. We know that this series diverges, and it's our harmonic, or we could say by p series. So those tests we were doing last time, this is where we need them. So we do not want to include -1 as an endpoint. We also have to check x equals -2. And we do the same thing, except we're plugging -2 in. And see if this converges or diverges. Well, now we have -4 plus 3. So this actually ends up becoming -1 to the n over n from 1 to infinity. This one is an alternating series. Alternating series, there's two things we have to check. Limit as n goes to infinity, excuse me, of 1 over n, that equals 0, check. And the other, well, we have to show that 1 over n plus 1 is less than 1 over n. Well, if we flip both those, we know that n plus 1 is greater than n. And so a sub n plus 1 is less than a sub n. That's part 2. So this is convergent by our alternating series test. So we do want to include -2. We could also do it. We could also do it in interval notation. -2 to -1, and a bracket and a parenthesis. What that tells us is this power series converges over this interval, including -2, but not -1. Any x values in that interval, this series will converge. Now, I'm going to give this a little bit more meaning later when we start talking more specifically about Taylor polynomials and Taylor series. But for right now, here's what I want you to take away. If we're given a power series, which is a series that has an x in there, and it's always raised to some power of n, it might be like to the 2n or something like that, it'll be very recognizable because of the x and then this nth exponent. And then there's going to be some other stuff going on. Not always, but usually. So there there are specific values of x for which they converge, and we want to find those values. So that's our goal with power series. Questions about this first example before we go on to another? Again, the nice thing about finding the interval of convergence of a power series is it's just applying the ratio test, which you've already had practice with. Now, when we do this, you probably noticed on the sheet here, let me make this a little bigger. And guys, like I said, always have this sheet when you're doing homework, when you come into class, because you're going to get these problems on the exam too. There's actually 1, 2, 3 cases, okay? We're going to go through each of those so that they make sense. Oh, let's do another example first, then we'll go through each case. Sorry about that. Okay, so this guy is what's called a Bessel function. It's a solution to a differential equation for planetary motion. This is a power function. It has that same x to an n power, and then some other stuff going on in it. This is a nasty looking function, and we want to find out where it converges. So let's put it on our slide here. We got x to the 2n plus 1. What I want to show you with this one is you don't let how much is going on in these things bother you. We do the same thing every time. Okay, so to find the interval of convergence, you do the same thing, but you apply the ratio test. So limit as n goes to infinity. Again, we do only include the absolute value this time. Because of the absolute value, we do not need to worry about the alternating term, just like before. Now, first thing is to put in n plus 1s every place there's an n. And I want to point out a couple common mistakes I see on this. So this one, this is going to be x to the 2 times n plus 1 plus 1. And we're going to have to distribute that too. So a common mistake is just to add 1 to this. You'll see how this ends up coming out in this way. This guy's going to be n plus 1 factorial. This will be n plus 2 factorial. And very similar to the top, this will be 2 to the, did I forget? Oh, sorry, this should have another 2 in there. 2n plus 1. 2 to the 2 times n plus 1 plus 1. That gets multiplied by the reciprocal of this guy. Again, don't worry about the negative 1 to the n term. Because of those absolute values, it is always going to go away in the ratio test. N plus 1 factorial, 2 to the n plus 1 over x to the 2n plus 1. Okay, first thing I want to do is I want to get rid of these parentheses. There is one cancel we can do right away if you want. N plus 1 factorial and n plus 1 factorial. That's totally fine. Let's start to clean this thing up already. It's a little bit less writing. Okay, when you distribute this 2, you're going to have 2n plus 2 plus 1. So that actually becomes x to the 2n plus 3. And again, that's one of the bigger mistakes I see when you got the 2 in front of the n. Remember that what you're doing is replacing n with an n plus 1, and then you have to FOIL in the 2. Okay, now we want some canceling to happen. So the n plus 2 factorial, well, that's n plus 2 times n plus 1, then times n factorial on n on down. And then very similar to this one, you got the 2n plus 2 plus 1. This is 2 to the 2n plus 3. N factorial, 2, gosh, I forgot to write the 2 there, I'm sorry. 2 to the 2n plus 1 over x to the 2n plus 1. Okay, very obvious cancel on the n factorials, great. These are going to have some canceling because we have the same base. But I just want to show you how the canceling is going to work out. Let's just do it off to the side here. Note, x to the 2n plus 3 is equal to, that's 2n plus 3 x's. We can rewrite that as x to the 2n plus 1 times x squared. Because two things are the same base, their exponents add. So if we were going the opposite direction, we can see how we get the 2n plus 3. So When this cancels, all of those are gone, and we're going to get left with two x's. Very similar, right? We're going to have two n plus 1 2's. It's going to leave us with two 2's on bottom. So there's all of our canceling. Now, just like I did before, I'm going to pull out anything that doesn't depend on n. The x squared and the 2 squared. X squared over 2 squared, which will change to 4 in a second. Now, like, if you remember last time, I put this in absolute values. Because it's x squared, you don't need those absolute values because x squared is already always going to be positive. It does not make it wrong if you do, but you don't need them. And what are we left with in terms of n? Limit as n goes to infinity of 1 over n plus 2 times n plus 1. Where does this limit go as n goes to infinity? Right? We're going to have something where the denominator is going to grow and the numerator's not. So what is the value of this limit? The value of this limit is 0. This is our favorite case because remember, we want this thing to be less than 1. If this thing is 0, then it doesn't matter what x is because this is 0. This is going to force whatever we let x be, whatever constant, this is going to force it to converge. So our interval of convergence is negative infinity to infinity. Okay, so this is another case. So we have two cases so far, and we'll do the third case here in a little bit. Case number 1, you take that limit and it comes out to be a constant. If that's the case, you're going to get some finite interval where you have to check the endpoints. Case number 2, this limit goes to 0. You don't have to do any more work. The interval of convergence is negative infinity to infinity. Done. We're going to have one other case, which is when this limit goes to infinity, and we'll cover that case in an example in a second. Questions about this example? All right. Then, let's generalize this. And after that, we'll go through an example where it's infinite. So, given the power series, this is any general power series, we have three possibilities for the radius of convergence and the interval of convergence. Now, we've done interval of convergence. I'll talk about radius of convergence here in just a second. So the series converges only when x equals a. That's the case we have not done yet, but I'll do one here in a couple minutes. Then the radius of convergence is 0. All right, we'll see that one shortly. 2, the series converges for all x. This is our example in purple. Then the radius of convergence equals infinity. So the interval of convergence is all reals. The radius of convergence is infinity. Lastly, there's a positive number r such that the series convergence if x minus a is less than r and diverges if x minus a is greater than r. So let's talk, that's this case. Now we know that the interval of convergence is -2 to -1. The radius of convergence, what it does is it talks about how far to the right and left of A. A is where we consider these power series centered. Same with Taylor series, they get centered at a value. And the radius of convergence is how far to the right or left these things converge. So if what we wanted was the radius of convergence, I'm going to show you two ways to come up with it. Number one, we would do it at this, we could do it at this step right here. What we would do if we wanted the radius, we would take this and notice the a is there, but there's no coefficient on x. So whatever x is being multiplied by, you divide everything by it. So in this case, we would divide everything by 2. So what would that do? That would leave us with x plus 3/2 is less than 1/2. That 1/2 is our radius of convergence. Then if we look, remember these things are centered at A. So when it's written in as x minus A, we would say it's centered at A. Well, we have x plus 3/2. This would be the same as saying x minus a negative 3/2 is less than 1/2. So this one is centered at negative 3/2. Well, look at our interval. Negative 3/2 lies right in the middle of our interval, so that's where it's centered. And then 1/2 in either direction, right? If we think on our number line. So here's our A, it's at negative 3/2. We know our interval of convergence is -1 to -2. And if we want to be specific, not included, included. But look at the distance from our center point, right? That distance is 1/2, and this distance is 1/2, even though that doesn't look like a 1/2 there. That's what the radius of convergence tells us. How far to the right and left of center our series converges. So radius of convergence and interval of convergence are two sides of the same coin. They talk about where these things are converging, just represented differently. One is represented as a single value versus an interval. And with interval of convergence, because we're looking at the interval, we have to check the endpoints. With radius of convergence, we don't. Now, I want to do an example of case number 1, so you can see what that looks like. So we're not going to go through all of these examples right now. We'll come back to these probably on Tuesday, just because we haven't had a lot of practice with this yet. But I'm going to do one of them. Now I'm going to pick it because I want something to happen. The nice thing about power series, to find the radius or interval of convergence, your first step is always the same. Run it through the ratio test. So limit as n goes to infinity, absolute value of a sub n plus 1, 3 to the n plus 1, x minus 1 to the n plus 1, and n plus 1 factorial. There's nothing really in the denominator, so let's just put it over 1, and then we'll multiply it by the reciprocal. 3 to the n, x minus 1 to the n, and then just n factorial. At this point, we're getting pretty good with the simplifying. So we know that 3 to the n is going to take up n of the 3's and just leave us with a single 3. The n x minus 1 is going to take all of those and just leave us with an x minus 1. And then the n factorial is just going to leave us with the n plus 1. Similar canceling. The canceling is pretty similar in a lot of these. Okay. And I'll do it in 2 steps because I wrote the limit a little too soon. So now we've got the absolute value of 3 times x minus 1. This is all we're left with. The only thing that depends on n is the n plus 1. Oops, that should be an absolute value, sorry. The 3 is always going to be positive. You don't have to worry about that in an absolute value, but the x minus 1. The only reason we got out of the absolute value last time is because we had an x of n plus 1. So this is a very straightforward limit. As n goes to infinity, n plus 1 goes to infinity. So this thing is never going to be less than 1, except for in one case. Less than 1 if x equals 1. Because if x equals 1, that makes the whole thing 0. So this is our last case. It only converges when x equals a. We can see that 1 is where it's centered. So x equals 1 is the only place. So that actually is our interval of convergence, and our radius of convergence is 0. This is our least favorite case. So we don't want our power series to only converge at one point, but it happens. Our favorite case is when the radius of convergence is infinite, but you will see that 3 happens pretty regularly as well. So those are those 3 cases. Okay, let's talk a little bit about why we care, and then we'll jump into Taylor polynomials, Taylor series, and start to really get this stuff, see what's actually going on. Okay, all functions can be thought of as generalized polynomials. This is the brilliance of Taylor polynomials. We use a Taylor polynomial to represent any differentiable function. Power series and polynomials are very easy to integrate and differentiate. So, when we're just, we haven't gotten to differential equations. We're going to touch on it in a couple weeks. But one of the problems is that solutions do not come out to be nice functions. So what we can do, just like that Bessel function, we can approximate solutions using power series. Or, for example, the integral of e to the negative x squared, which is the motion of a pendulum. Well, the answer to that is not trivial, but a power series representation allows us something that we can easily manipulate and investigate. This is also how computers handle difficult computations. They actually use series. So there's a lot of uses for series in engineering, computing. They're very powerful. So, like I said, that was kind of our foray into what we're actually what you're going to look at lesson-wise on Tuesday, power series. So now let's take it back to Taylor polynomials. Now, before we talk about Taylor polynomials specifically, it turns out in Calc 1 you've already done Taylor polynomials, which is a tangent line. Now, it might be written a little bit different than you saw it in Calc 1, but this is going to lead very nicely into our Taylor polynomials. What this does is it forces us to match the function value and the slope at A. That helps us make this approximation. So what we're going to do is we'll do an example and see how building this up helps us. So we're going to do it at 0 for right now, but we can do this at any point depending on where we want it centered. So let's talk about doing sine near 0. So we start off with our sine function. And then what we do is we calculate its value at 0. Well, sine of 0 is 0. So nothing really added there. We also find the first derivative. Derivative of sine is cosine. And then we plug in 0 into that first derivative. Cosine of 0 is 1. So our first degree Taylor polynomial is 0 plus 1 times x, which just simplifies down to x. The nice thing about Taylor polynomials is they all build on themselves. Now, we're also going to be exploring the graph of this. So let's get a graphing window up here. Oops. so we can kind of watch what's happening. We'll just use Desmos for right now. Okay, so what we're trying to do is match sine of x. Okay, so there's our function. All right, so our first degree Taylor polynomial is just x. And if we zoom in, we see that it is a pretty good approximation locally, but it doesn't have any concavity. So we want to add in concavity. So what we're going to do is match the second derivative at a, or in this case at 0. Now, turns out that the second derivative, and the way we put this in is f double prime of 0 over 2. The second derivative of sine, unfortunately, is not going to make this one more interesting, because the second derivative is negative sine x. And so then second derivative at 0 is nothing added there. If we had a second derivative, we would have a quadratic. Now, what we need to do is start matching higher order derivatives. That's going to help make the shape match. So this creates what's called the Taylor polynomial of degree n, with this being the coefficient. Okay, and that's one of the things we're going to make sure we get a little bit of practice on today. But let's talk about how we use this. Okay, so we already know that the second degree Taylor polynomial for sine x is actually the exact same as the first degree, so nothing new there. So we're going to go to the third degree, which means we need the third derivative. All this stuff matches up. The degree tells you what derivative you need. Derivative of negative sine is negative cosine x. So now we evaluate that at 0, and we get negative 1. So look at how this term looks. It's the third derivative at 0 over n factorial x to the n. N in this case is 3. Third derivative, 3 factorial x to the 3. So the third degree Taylor polynomial for this one, oops, I wrote that out of order, excuse me, is x. Now it's going to be negative, so minus the coefficient, which is a -1, x to the third over 3 factorial. 3 factorial is just 6. X minus x cubed over 3 factorial. Now, we could start another polynomial, but all this does is add extra terms. So x cubed divided by 6, and I meant to write 6 there. Jeez. And now look at the match we get. It goes out a little bit further, right? Now we start to get some of that concavity. The higher the degree, the better the match. And we'll keep going with sine of x. Now, something you're going to notice pattern-wise is every time we take an even derivative, we get either sine or negative sine, which at 0 is 0. So the fourth degree is the same as the third degree. So we're going to go to the fifth degree, which again brings us back to cosine. And at this point, what's really nice is if if we're going to keep going by hand, we see a pattern forming, right? 0, 1, 0, negative, 0, 1, 0, negative, 0, 1, 0, negative. So our fifth degree Taylor polynomial, it's our third, which is x minus x cubed over 6, plus this additional term, which is now a +1 over 5 factorial times x to the 5th. So 3 factorial is 6, 4 factorial is 24, 5 factorial is 120. So we need to add that next term, which is x to the 5th divided by 120. And again, notice how our polynomial converges to our sine curve even more. And we can keep going on this. It gets better and better. And, you know, we can already see the pattern. So I just want to show you how this happened. But this is done in a program called Maple. But I'll show you how to do this in another program here in just a second. Okay, so we already did the first degree. We know what that looks like. Okay, here's the third degree. We know what that looks like. We saw this one, the 5th degree. Now let's really start upping the degree. In other words, because I'm using Maple, I can do it very quickly. Here's a 9th degree. Now we've got a match for an entire period of sine. If we want to get really extreme, we can actually, let's do this. Let's make this 20, which makes this a 19th degree Taylor polynomial. From negative 2 pi to 2 pi, we get the exact same graph. Remember, here's what's so incredible about this. We took a trig function, and this is actually a polynomial put on top of it. Now, I'm only looking from negative 2 pi to 2 pi. If we actually start to zoom that range out a little bit, we're going to see where it stops matching. But it turns out, if we look at the infinite Taylor series for sine, it actually maps 100% to the sine curve. But it has to be infinite because sine goes on infinitely in both directions. So that's the main thing behind these Taylor polynomials. What they do is they allow us to use a polynomial to model functions that aren't polynomials. Right now we're just doing a basic one like sine x, but we can do this with much more complicated functions. So that's the true power of these Taylor polynomials. Because again, polynomials are much easier to deal with. All right, so now we want to talk about these things in general. They do not have to be centered at 0. So they can be centered anywhere we want, just like we were seeing with the power series. A is where we're centering. That one happened to be centered at 0. We'll look at one centered someplace else here in a little bit because it kind of helps. You know, depending on what we're trying to do, we may not want it centered at 0. We may want to move it around because that may be more useful for us, depending on what we're trying to approximate. Okay, so we saw this. We saw some, you know, and the nice thing about sine is there's a nice pattern forming here, right? It's an alternating series. The exponents go up by 2 each time, and the denominator factorial goes up by 2 each time. So we can write this up as a series for sine of x as the following. Now, here is why this is why I like talking about power series and radius of convergence first, is now that we have this written up in summation notation, we can find the interval of convergence for sine. Now, based on what we already looked at graphically, we probably have a pretty intuitive idea because we saw that thing was going to converge to infinity. We're going to expect the radius of convergence to be infinite, but let's make sure we can show it. So used k there, so let's use k here. K equals 0 to infinity. -1 to the k. X to the 2k plus 1 over 2k plus 1 factorial. So limit as n goes to, not n, using k, excuse me. Limit as k goes to infinity of the absolute value, Remember, we don't need to include the alternating piece. We'll put in k plus 1s every place there's a k. And like we saw before, because of this 2, when we put in that k plus 1, we're going to get x to the 2k plus 3. So that's the same as the one we looked at previously. Over 2k plus 3 factorial. And this is times 2k plus 1 factorial over x to the 2k plus 1. Now we go into factoring mode. Very similar factoring, but I'm going to write it out on this one. That becomes x to the 2k plus 1 times x squared. This part we're leaving alone for right now. We're going to start to expand this guy. So 2k plus 3 times 2k plus 2. The next term is 2k plus 1. So we'll stop there because that's enough to get our cancel. And this is our x to the 2k plus 1. This makes our canceling very obvious. Those and those. The x squared does not depend on k. Because it's x squared, you don't need the absolute value. Limit as k goes to infinity of, what do we have left? Oops, don't need the absolute value for this part either. Again, it doesn't make it wrong, but we don't. 1 over 2k plus 3 times 2k plus 2. So once again, we have a situation where the denominator's growing and the numerator's not. This limit goes to 0. So this thing is going to be less than 1 for all real numbers. So that's going to be our interval of convergence. Or if we wanted our radius, it'll be infinite. Not a huge surprise, right? It matches up with what we were seeing graphically. But we are able to mathematically show what we saw. Then, this will be a cool, this I think is kind of an interesting example. Oh, sorry, we're not at the example yet. We talked a little bit about the Taylor polynomial. The Taylor series is the infinite series made up of the Taylor coefficients. This is what's called the Taylor coefficient here. F to the n of a, n factorial. You use these a lot, so it's going to be something that you're going to want to remember. But because you're going to find so many in the homework, you get very used to it. We want to make sure that we know this form for a Taylor series. So what we'll do is I'll do one, and then maybe we'll do an example together. All right. So let's see, we're going to do the Taylor series of ln of x about a equals 1. We're going to find the first 5 non-zero sums and write it in summation notation first. All right, so let's see what this looks like. So f of x equals ln of x. And again, this one we're doing around 1 instead of 0. So we need the first 5 non-zero terms. So we need the first 5 things that don't come out to 0. So we know that f of x equals ln of x. And f of 1 is ln of 1 or 0. So we're still going to need a few more derivatives. So f prime of x. 1 over x. F prime of 1 is 1 over 1, which is 1. Now, on a lot of these, there will be patterns to be recognized. Here's what I'm going to do here. Is I'm going to change that x to the minus 1 because I don't want to lose the negatives. Some very interesting stuff going on with that. F double prime of x will be negative x to the negative 2, or negative 1 over x squared. So f double prime of 1 is negative 1. F triple prime 2x to the negative 3. We're going to get a lot of practice with derivatives in this section, which is 2 over x cubed. So the triple prime at 1 goes back to positive, so we're going to have an alternating series, but it ends up being 2 over 1. F to the fourth derivative, negative 6, x to the negative 4, the fourth derivative evaluated at 1, so it's a 4, not a 9. I mean, anytime we put 1 on this, it's just going to come out to be 1, so it ends up being negative 6. The fifth derivative, negative 4 comes down times the negative 6, we get a positive 24, x to the negative 5th. So the fifth derivative at 1 is 24. We have 1, 2, 3, 4, 5. So this is enough to get the first 5 non-zero terms. But if it weren't, notice we have a pattern going on. First off, the signs are alternating, positive, negative, positive, negative, positive. And 2 is 2 factorial. 6 is 3 factorial. 24 is 4 factorial. So without doing any other work, we know that the sixth derivative at 1, well, it alternates back to negative. And now it'd be 5 factorial, which is 120. Not that we need that for this problem, but there's a lot of patterns going on here. So recognizing them helps us do some of these problems quick. They happen quite often. Now let's talk about how we put a Taylor polynomial together. Okay, so we use our Taylor polynomial. So let's go back to the general. Now in our case, a is 1. So the first thing is f of a. Well, that came out to be 0. Not very interesting. Plus f prime of 1. So 1 times x minus 1. That's this term here. This is our tangent line. Then we go up to a quadratic. So we're going to have negative 1 over 2 factorial times x minus 1 squared. I'm going to have to go to the next line. So plus. We'll do all the negatives and everything here in the next step. Now we go to the third derivative, which is a positive 2 over, it's the third derivative, so 3 factorial times x minus 1 to the third. So there's a very consistent pattern going on here. So now negative 6 over 4 factorial times x minus 1 to the fourth. We have 1, 2, 3, 4 terms. We need one more. So lastly, we'll be back to positive 24 over 5 factorial x minus 1 to the fifth. So again, there's a lot of things matching. So it's going to take a little bit of practice for you to get used to these coefficients and these terms, but they're not that hard because they just keep following the same pattern. Now let's see if we can simplify this thing a little bit. Let's it's the same one. Well, we don't need the 0. We don't need to write out the 1. So we have x minus 1 minus 1/2. 2 factorial is just 2 over x minus 1 squared. 2 over 3 factorial. 3 factorial is just 6. Or this is 3 times 2. So cancel out the 2's, you get 1/3. So plus 1/3 times x minus 1 cubed minus 3. This is basically 3 factorial, 4 factorial. So actually all you get left with is 1/4. And now we really start to see the pattern here. Not all of them have as nice of a pattern as this one. Obviously, the more complex the function, the more complex the Taylor polynomial. But a lot of them do. So we want to recognize patterns whenever possible. Again, this is 4 factorial over 5 factorial. So 1/5. The nice thing is, if we need any more terms, we know the pattern. Next term is 1/6, is negative 1/6, x minus 1 to the 6th. So on and so forth. So these will be the first 5 non-zero terms, which gives us a 5th degree Taylor polynomial of our function. Next thing we want to do is figure out where this series converges. Well, to do that, we have to write it up in summation notation. We have a very obvious pattern going on here. So we want to write this up in general summation notation. We see that it's alternating. So we're going to have a -1 either to the n or n plus 1. We'll decide that in a little bit. We see that there's clearly an x minus 1 to the n, and that it's basically being divided by n. Now the only problem here, we'd want to start this at n equals 1. Now everything's going to check out. The only problem is, except for this one, because that's going to force this to start on a negative. So all we have to do to fix that, add 1 to the exponent, that makes it start on a positive. So that would be the infinite series of ln of x centered about 1. Now, the advantage of doing that, we can now find the interval of convergence, or the radius of convergence, whichever we're interested in. Limit as n goes to infinity. Remember, we don't have to include the alternating piece. X minus 1 to the n plus 1, excuse me, over n plus 1, and then the reciprocal, n over x minus 1 to the n. And similar canceling before. There's nx minus 1s here. There's n plus 1 of them there. It's about all the canceling we can do. But that allows us to pull that x minus 1 out. And we got the limit as n goes to infinity of n over n plus 1. We saw that one before. We know this goes to 1. So the absolute value of x minus 1 has to be less than 1. That means x minus 1, or no, it means x minus 1 is in between 1 and -1. Add 1 to get our interval for x. It has to be in between 2 and 0. Now, this is again a case where we have to check the endpoints. So we have an endpoint at 2. So if x equals 2, we plug it into our series. And 2 minus, well, let's plug it in so we can see how it simplifies. -1 to the n plus 1 times 2 minus 1 to the n over n. 2 minus 1 to the n is just 1 to the n, 1. So this whole part disappears. So this is just the alternating series -1 to the n plus 1 over n. We saw that earlier. One converges by alternating series test. Normally, we would go through showing the steps in a proof. But for what we're doing right now, we showed this exact one earlier. So we know we want to include 2. Now, when we do 1, something really interesting happens with 1. And we'll see graphically why it makes sense. So when we put in 1, sorry for writing at the very bottom here, n plus 1, when we put in, when we put in 0, not 1, 0, we get 0 minus 1 to the n over n. Well, here's what happens here. We have negative 1 to the n plus 1 and negative 1 to the n. Two things of the same base. We could add their exponents or think about what's going to happen. Basically, whenever this one is negative, this one will be negative. These are basically going to cancel each other out. It's either always going to be negative or always going to be positive. Well, we're starting at 1 to infinity. So one of them is always going to be negative. So this literally comes out to be the negative of the harmonic series, which we know diverges. So our interval of convergence is 0 to 2. I know I went through that part a little bit quick, but it's only because we'd seen it before. Now I want to show you graphically what's happening. This is where I think, you know, to me, it really, the stuff really starts to make sense. So we're going to be graphing ln of x with its Taylor series. So here it is with its first degree Taylor series. There's ln of x. There's its tangent line. Okay, so we were doing a 5th degree, so let's get up to the 5th degree. But look at what's happening. Nice convergence here, but then it diverges. See a nice convergence here. So here's the 5th degree that we found. We see a nice bit of convergence here, but a divergence here. So what I'm going to do is drastically increase our Taylor polynomial. So this is a 35th degree Taylor polynomial. Look at what happens. That's the interval of convergence. That means our Taylor series, our Taylor series converges perfectly between 0 and 2. But notice what happens at 2. All of a sudden it diverges. The reason we don't want to include 0, ln of x is undefined at 0, so it makes sense that we don't include 0. But this is what that interval of convergence means. Now we saw with sine of x, it converged everywhere. But here, this is the case where we have a finite interval. This is the kind of stuff you see. It's, wow, it's a really good match. And then all of a sudden you get to a point where, whoa, they diverge. That's the meaning of this interval of convergence. The interval of convergence stays the same the whole time because the interval of convergence that we found was for the infinite Taylor series. So no matter how many terms we add to the polynomial, it'll never converge from anything outside of 0 to 2. We'll do one of these. Maybe we'll probably do either 1 or 3. But I want to show you something just so you can see it, and I want to get it on the record here. Like I said, I'm using a program called Maple to calculate my Taylor polynomials. You could get to Maple through MySCC, but I don't want you to worry about it. You know, deal with Maple. We don't need it, but we do have. I had it open, but I can't find it now. Okay, but we do have Wolfram. So let's do number 2 with Wolfram alpha. We want the first 4 non-zero terms. The first term would be non-zero. So we'd be basically looking at 3rd degree. You can literally type it in. And this is actually really impressive. There is your first 4 non-zero terms of this Taylor polynomial. It's centered at pi over 4. That's why we have the x minus pi over 4. Sine of pi over 4 is rad 2 over 2 or 1 over rad 2 from our unit circle. That's where the square root of 2 is coming from. And then 2 factorial. 3, 3 factorial. So that's basically where everything's coming from, excuse me, for this one. And the reason I'm showing you this is going to be great for checking your answers. We do need to be able to do Taylor series by hand. We need to know how they work. We need to be familiar with that coefficient. It's actually very important. But I also want you to have the ability to check your answers whenever possible. So Wolfram Alpha is something that can do that.